Good evening, Amelia. How are you?
Hi, Edward. I'm good. How are you?
I'm also well. Just trying to keep warm, but it
Is it
is,
cold back home? Well, we'll be heading there in a bit, so I'm going to probably freeze.
yeah, hopefully when you get back, it won't be as cold as it is now. Um,
Listen, winter is until August, right? So I think it's still going to be quite cold by the time we get home.
yeah, and then maybe you'll just catch the tail end of
The
winter,
tail end
and
of it.
then
I hope so.
yeah, yeah. All right. I think I'm going to get started because it's 8 o'clock
All
now,
right.
and the recording is underway. And this is the last session for us. So hopefully you found the sessions useful, and hopefully what we covered tonight would be also useful for your remaining parts of Unit 7. All right. So we are going to get started, and we are looking at sections 11.5, 12.1, 12.2, and 12.7. This is also part of calculus, and I just want to advise you to also pay special attention to your assignment because I know that last one carries a lot of marks, so it's a huge chunk of your marks. So yeah, let's get into it. I will also try and aim for this session not to keep you for too long because last time I explained too many things and then we ended up rushing the last part of it. So I did write the solutions before, so we'll do it kind of like a discussion with some explanations in between. All right. So the first problem is problem number 8, and it is asking us to use the chain rule, and it gives us the chain rule in its most basic form so that we get to practice it because we'll be using it quite a lot in later problems. But then they tell us that if you are given y as a function of u and u as a function of x, find dy dx. All right, so you have y as some function of u and u as some function of x. So now you want to connect this y and the x and then find dy dx. So you're going to use the chain rule to get dy du and then use and again find du dx, and then the chain rule would be dy du times du dx. Right? So you see the du and the du cancel there, and then you end up with dy over dx. This is the chain rule. This is your first chain, that's your second chain, and that's how we would do it. Right? So let's just go and find dy du and substitute in there and find du dx, substitute there, then multiply the two. All right, so dy du is just differentiating y with respect to u. So this would be 3 times 2, that's 6u. 3 minus 1 is 2, so 6u to the power 2, and then 6u to the power 1 plus 5, and that's what we have there. And then if we differentiate u with respect to x, we'll have 3 times 1, so that's just that. Okay, and then you multiply the 2, and then you will have dy dx, but now we have it in terms of u, but we don't want this substitution variable. We're going to write it in terms of x. So we replace everywhere where we see a u with 3x plus 1 to get okay, so the other way we can do is doing that. Everywhere where there's x, you replace with 3x plus 1, or you can say, okay, when x is equal to 1, u is equal to 4, and then you do the substitution. So this says dy dx when x is equal to 1. So that's that notation, dy dx evaluated when x is equal to 1, and then you substitute directly into what we calculated there. What I was talking about was you would also be able to write dy dx in terms of x. So you will have 6 3x plus 1 squared plus 6, 3x plus 1 plus 5, all times 3, and then you substitute this x equal to 1 into there to get dy dx when x is equal to 1. So the same answer will be your result as we found there. All right. So now we proceed to the next problem, which is problem number
Okay,
40, which is
sorry.
just, yes, please
Sorry,
ask.
Edward. Just a quick question. On the above one, when you did it 6, 3x plus 1 squared, the top bracket dy dx, when you substituted u into the x, would you work the
Hmm.
brackets out first? So when you have 6 multiplied by 3x plus 1 all squared, would you work that squared bracket out first, or would you
So,
multiply by the 6 first?
so
Or does it not
actually, I
make a
would.
difference?
In this case, it does not make a difference to do any simplification before you do a substitution of x equal to 1, because this question just ideally says find the derivative when x is equal to
Okay.
1. So they just want to find the answer when x is equal to 1. So you'll find that if you simplify all of these things, it might take you an extra 2 minutes to do that. And then you'll substitute the 1, but you'll still arrive at
At the
the
same,
answer of
okay.
300. Yes. So when we do a lot of these questions for calculus and finding derivatives, um, we normally set, especially assignments, to say, do the derivative, don't bother simplifying, right?
Okay.
Because simplifying, we know you've done the algebra, we know we've done it in the A module, and you can do simplification, you can multiply out brackets and all of that. We just now want to see if you can find the derivative.
Okay.
But yeah, under normal circumstances, like if you're writing an exam and so on, you always have to simplify your answers, but we do specify when we don't even want to see any simplification because we know that just wastes time. You've done the derivative and we know what you know what you're doing. So yeah. All
Thanks.
right. Pleasure. Okay, so let's proceed to the next problem, which is asking us to find y prime. So that's just another notation to say dy dx or the first derivative. Right, so find the first derivative when you're given y is equal to 3x plus 2 to the power 5 times 4x minus 5 to the power 2. So this, if you inspect what y looks like, we see you have these two brackets. So you have a multiplication. So we are going to need to use the product rule, firstly. And then secondly, for each of these two brackets, you see there's 3x plus 2 and it's to the power of 5. Here there's 4x minus 5 is to the power of 2. So in these two cases, we will need to use the chain rule because there is some function of x, but it is to the power of 5. So there's a function inside a function. The outside function is this function that takes everything and it makes it to the power of 5. The inside function is this 3x plus 2. So you would break it down into a chain rule and then you would also use the product rule. Right. So let's go and proceed by first doing the product rule because there are two things multiplying each other. And depending on how you want to do the product rule, um, I'll call this maybe u, this bracket, u, and I'll call that one v, right? So this whole thing to the power 5 and that whole thing to the power 2. So that's our u and our v. So we have some y equal to u times v, right? So the product rule says that you need to take, so y prime would be equal to, you take one of them constant, and then you multiply by the derivative of the other one, plus now you keep the other one constant, the one that you differentiated before, and then you multiply by the derivative of uh, the other one, right? So u v prime plus v u prime. Okay, so you'll see some people will do it like v u prime plus uv prime. It doesn't matter because there's a plus there and there's a plus there, so you can interchange these two things. So I'm going to start by keeping the first bracket constant, so 3x plus 2 to the power 5. I'll keep it constant, and then I'll differentiate the second bracket. So I'll differentiate this one. To differentiate it, we need to use the chain rule. So the outer function is this 2. So we differentiate something to the power of 2. So we know that we bring the power down. So that's 2 multiply by the whole bracket to the power of 2 minus 1. So that 2 minus 1 is 1. So that power is 1, which we normally don't write. And then the second chain would be differentiate the inside function, right? So 4x minus 5 when differentiated gives us a 4. And then you have your two chains multiplying each other, right? So this is product rule. And then if you write a chain rule on the side here, just to reiterate what we did, if we have y equal to some function of u and u equal to some function of x, chain rule would be dy dx equal to dy du times du dx. So our whole function is we differentiated this outer function. So that would be our f, and then we multiply by the differentiation of the inner function, and that would be our g. So you see our u is the inner function, our f is the outer function, and then we just multiply one chain times the other chain. And then plus we do the second part of our chain rule. The second thing that the v is the second bracket, so we keep that constant. Then we multiply by the differentiation of 3x plus 2 to the power 5. Again, we use the chain rule. The 5 goes down and multiplies the whole bracket, so there's the 5 times 3x plus 2 to the power of 5 minus 1, which is 4, times the second chain is differentiate the inside function. So if you differentiate 3x plus 2, you get 3. Right. At this point in your assignment or whatever, if we give you a rule and say, don't bother simplifying, you would even leave it here. But in the solution that I will post for you, I go and I simplify. But all of this is just now algebra, differentiation, or let me just say simplification. The only calculus happened here. So this was where we actually did the differentiation. Okay. So I would go and I would say, I'll give you a mark for keeping that constant. I'll give you a mark for doing that chain rule. I'll give you a mark for that. I'll give you a mark for that. Or more marks if I'm maybe marking part things as well. Right. So hopefully that makes sense to everyone. It was a bit of a couple of rules happening at the same time, but that's how we would approach that. Okay. So now we proceed to the next question, which actually I realized after setting this session that it's not in the scope of this module. So I will skip problem number 66, which is about a marginal revenue product, but you can review it for interest sake if you have the time, but it's not in the scope of this module. I reviewed your lecture videos and I think it's the same as example 8, and Mr. Van Reenen says it's not in the scope, so we'll skip this. It's just about marginal revenue product, so that is not in your scope. It's just an application, so I'm going to write application of the chain rule. Okay, right. Okay, so now we move on to section 12.1, problem number 20. Which is asking us to differentiate the function, and if possible, first use properties of logs to simplify the given function. And our given function in this case is y equal to x squared over ln x. This one, if we inspect it, we see we can't really simplify it any further, so we will proceed and do the differentiation. So we notice here, firstly, that we have a quotient. So we will need to use the quotient rule, right? So we have a fraction, so that's going to make us use the quotient rule. And then we also have a log there, a natural log, so we will need to use that ln rule or the rule for the log. So differentiating a logarithm, we know what to do with that. So those are the two rules that will come into play. The other rules are the basic ones like differentiating x squared, we know is the power rule and so on. So we're going to do that. So firstly, if we have a quotient, so I'm going to call that u and v. Our numerator is u and our denominator is v. For the quotient rule, y prime would be v times u prime minus u times v prime, okay? Divided by the square of the denominator. So that is the quotient rule. So let's go ahead and do this, okay? So it's always important to remember your rules. You can even write it on the side for yourself, and then you go and you calculate u prime, you calculate v prime, and then you just substitute into your formula. But we'll do that now, step by step. So we notice that in our numerator for y prime, for dy dx, we're going to have v. So v is just linear x, so we write linear x times u prime. So we differentiate x squared and then we get 2x minus, we take u as it is, so x squared times, we differentiate v, so it's differentiating ln x. A differentiation of a log, so it's always 1 over whatever we have as the argument of the log times the differentiation of that thing. So it'll be 1 over x times differentiation of x is 1, so we didn't even write it there. And then all divided by the denominator, or v squared. So you take ln x and then you square it. At this point, this is the only differentiation part that is in this question. The rest is simplification, right? So this is just simplifying to write your answer in a simple or in an easier to read manner, right? So it's just simplifying the numerator, and then we can't really do anything about the denominator, all right? So that's just simplification, and you can review that when you see the PDF. Okay, hopefully everyone is fine at this point. All right, perfect. Right, I'm going to move on to problem number 30. This problem is asking us also to differentiate the function and, if possible, use the properties of logs to simplify and then differentiate. So we have a look at this one and we notice that there's ln of a cube root of a fraction, right? So there's going to be a couple of rules in play, but then before we even go ahead and do the differentiation, we can actually simplify this to make life a little bit easier for ourselves, because there is a natural log there, and then there's a radical. So we can write that as ln of a fractional exponent instead of a radical. So we have x cubed minus 1 over x cubed plus 1 all to the power of 1/3. Right? Now we know that we can simplify further by making this power the coefficient of this log. So that would be 1 over 3 times ln x. I'm saying x and I'm writing the next thing that I'm supposed to write. So x cubed minus 1 over x cubed plus 1. And we can go one step further, because we have a fraction and we don't necessarily want to do a quotient rule, because that just complicates our life. We can even make it simpler by saying, okay, so 1/3 times ln of the numerator minus ln of the denominator. So that's ln of x cubed minus 1 minus ln of x cubed plus 1. And now all of a sudden, this thing looks much simpler to differentiate than if it was like that. Okay, so first of all, we've gotten rid of the radical, and secondly, we've gotten rid of the fraction of the quotient. So now all we'll need to do is use the log rule instead of using the log rule and the quotient rule at the same time. So if we go ahead and do that, so we'll see we got to this point when we were working out here at the top, and we'll simply now just differentiate that. So you'll know if you have a constant times a function, when you differentiate, uh, dy dx becomes the constant times whatever the differentiation of the inside is. So we'll differentiate term by term. Remember the sum and the difference rule. You differentiate that minus, you differentiate that. Okay, so firstly, if we differentiate that, we know the rule for logs or for the natural log is that it's always 1 over whatever is inside times the differentiation of whatever is inside. So let's do the first part. So 1 over whatever is inside, so that's x cubed minus 1 times the differentiation of what's inside there. So x cubed minus 1 when differentiated is 3x squared minus 0, which is just 3x squared. So it's just a chain rule that's applied onto logs. And then we go and do minus, and then we do the same thing for that. It's 1 over the argument of the log times the differentiation of the inside function. So that's 3x squared again. Okay. And this is where the differentiation happened. And the rest is simplification. And it actually simplifies to a very nice looking fraction that is not 1, 2 terms times a constant. It just simplifies to that. Okay. So please just bear in mind if you're told not to bother simplifying, don't waste your time doing that because we know you are capable of doing that. But if you don't get that instruction, please do go ahead and simplify. All right. So now we move on to problem number 48, which is about marginal revenue. So remember what we talked about last time. Marginal just means find the derivative, and the derivative of what in this case is the derivative of revenue. Okay, so you want to find R prime, and um, in this case we know our revenue is P times Q, and we are given P. We just need to multiply this by Q, and then we go ahead to find marginal revenue, which would just be dr dq. Okay, so simple steps. Let's go and find our R, that's PQ. We multiply this by Q, so we end up with 50Q over ln of Q plus 3, which is just a quotient or a fraction that also has a ln inside it or log inside it. So we're going to use two rules. Firstly, the quotient rule, and secondly, the log rule. So we're going to go ahead and do that. If we use the log rule, so I just rewrote this to take the constant outside so that we don't need to carry the 50 everywhere we go. We'll get the same solution if we kept the numerator as 50q, okay? So the 50 is outside, and then we differentiate. This is our u, and that's our v. If you take v times u prime in the numerator, so that is v times u prime. If you differentiate q, you get 1 minus, and then you do u times v prime. So u is q, so q times the differentiation of ln of q plus 3. It's 1 over q plus 3 times the differentiation of q plus 3, which is 1. So we end up with 1 over q plus 3. And then the bottom, the denominator, we just square whatever v was to end up with ln of q plus 3 all squared. And that's our differentiation. And this is the simplification. Okay, so when we're simplifying, we just made, see there is a fraction on top of a fraction. So there's a fraction in the numerator. We multiplied everything by q plus 3 so that we don't end up with a fraction. And we ended up with this result. Okay. All right. So that was that problem. And then we want to differentiate in section 12.2. Now we have an exponential function, and in this case, so we know we're going to use the exponential rule, and then also we have an inside function and an outside function. So we're going to use the chain rule again with this exponential rule. And I quite like differentiating exponential functions because whatever the function is, you get the same function back, unless if you're dealing with a function inside a function. In this case, even the exponential function has another inside function. So let's go ahead and do that. You would differentiate by means of the chain rule, the outside function first. So y prime would be this function to the power 3. So 3 becomes a coefficient times whatever's inside. So that's e to the 2x plus 1. And then to the power of 3 minus 1, which is 2, times. The second chain now is differentiate the inside. If you differentiate e to the 2x plus 1, you get, firstly, when you differentiate that, it's e to the 2x. So that's e to the 2x. But there's another inside function. So that was the outside function. The inside function is 2. So you multiply that again by differentiation of 2x. So that's just 2. And then if you differentiate plus 1, you get nothing. So we end up here. All right, so that's the differentiation, and the rest is simplification. Obviously, you would multiply the 2 and the 3 to get a 6. And I normally like to write the e to the 2x first. So e to the 2x, and then I'll write the bracket e to the 2x plus 1 to the power 2. And we'll see that's where we end up there. All right. Okay, so if we then proceed to the next problem, I think it's going to be, okay, so it's an application type problem. So we are given the average cost of producing Q units of a product, but we want to find marginal cost. So again, marginal means differentiate. And what do we differentiate? The cost function. So we are given the average cost function. So we need to find the cost function first. We know average cost is just your cost divided by the number of your units. So for us to actually get the cost function, we just take our average times Q. So we can do that because we are given our average cost function, which is this one here. If you multiply that by Q, it just means that we are getting rid of these Q's in the denominator. So it's quite nice. And after we do that, we differentiate that C. So we do d C dq. And then, so that's the first thing that we need to do. The second thing that we need to do, and the third thing we need to do is to evaluate our solution when Q is 97, and then also when Q is 197. So those are the steps we'll take. The first step, second step, the third step. So let's go ahead and do the first step, which is quite easy. We did it already when we were talking. Multiply by Q, and then we get that as our function for cost. So this is our cost function. I just simplified this power for the exponential because 2q plus 6 does factor out to give us 2 times q plus 3 all over 800, which is just q plus 3 all over 400. Okay. And secondly, to get our derivative, we just differentiate this with respect to q. Obviously, when you differentiate a constant, it falls away. Plus, when you differentiate constant times an exponential, we get the constant times the differentiation of the exponential function. So that's 4,000 times, if we differentiate e to the q plus 3 over 400, we get e to the q plus 3 over 400 times the differentiation of the inside function, which is 1 over 400, right? So let's just show that there. So q plus 3 over 400. If you differentiate this with respect to q, right, you will notice that, so d dq, if you differentiate this, you'll notice that you're just differentiating 1 over 400 times q plus 3. So this constant is just a constant, so your answer will be 1 over 400 times the differentiation of this, which is 1 plus 0, which is just 1. So you end up with 1 over 400. Right? That's how I got this over 400. Okay. So we've differentiated this and that, simplified to become a 10, and That's 10e to the cube plus 3 over 400. And then now we just do the step 3. So that was step 2, step 1. Step 3 is just evaluating at these two different values. It's just simply putting 97 wherever there's a Q here. And then you find out, okay, that's your answer. I didn't bother to go and find the actual value by multiplying e to the 0.25. I prefer to keep it as an exact answer because we're not going to do anything with the value after that. And I substituted 197 and we got that, and we're done with that question. Okay. Right, so we'll move on to the next section. So problem number 2 for section 12.7. I think this section is actually the higher order derivatives, which is nothing but practice of what we already know. So higher order derivatives are just uh, doing derivatives repeatedly. So if I ask you for the third derivative, it is just differentiating 3 times. So you get the first derivative, and then you differentiate your derivative again to get the second derivative, and then you do the process again to get the third derivative. So this is just now practice. Um, I know higher order derivatives have different applications in different fields, but at this point, we will just emphasize what they are and just practice them. And you will find that this is nothing new. So find the indicated derivative. Here is the third derivative. So we have to find y prime, then find y double prime, then find y 3 primes. Okay, so that's the third derivative. Third derivative. Okay, and if I do ask you to do this in an assignment, for example, please don't go and calculate on a paper on the side and then just write the answer for the third derivative without showing your first and your second derivative, because I do give some marks for your first and your second and your third derivative as well. And also I like to do that because if you make a mistake, let's say somewhere here, you won't lose marks for me knowing that you can do the derivative for the first one. So yeah, just something to note. Okay, so this one, the first derivative, this is just a polynomial, so it's quite easy to do. It's just powers of x. So the first derivative would be 5x to the 4 plus 4x to the 3 plus 3x to the 2 plus 2x plus 1. Right, so that's that one. If we do it again, if you differentiate your first derivative, you get your second derivative. So this would be 20x to the 3 plus 12 x to the 2 plus 6x plus 2 plus 0. Okay, so we get that. And then we differentiate again to get the third derivative. And please, when you're writing out stuff, please don't say, okay, y is equal to this, and you go equal to get the derivative, you go equal to you get the other derivative, because that's not y anymore. This is y prime, this is y double prime, and the next one is y 3 primes, which is the third derivative. So that would be 3 times 20, so 60x to the power of 3 minus 2, which is 3 minus 1, which is 2, plus and so on. So 24x plus 6. And then you get your third derivative. Right. So if you wanted to get your fourth derivative, uh, so y, so I'll just do that. Your fourth derivative, that would be 120x plus 24 plus nothing, and so on, right? But we did ask only to get to the third derivative. Cool. Right, so we will go on to problem number 6, which is asking us to find, this is just another notation, this saying the third derivative, okay, of f. So we need to do df dq and get the first one, do it again, get the second one, do it again, get the third one, right? So just a different notation for the third derivative. Here we have a ln function, so a natural log. The first derivative would be 1 over q plus 1, right? If we do that, we check, okay, that's 1 over q plus 1. And I'm just going to rewrite it as q plus 1 to the power minus 1 because we want to get to a second derivative. So it's easier to differentiate exponents of something. So we do that. Second derivative would be minus 1 times q plus 1 to the minus 2, right? So we always minus 1 from the exponent. So we get to the minus 2. And then to get to our third derivative, it would be this minus 2 times this minus 1. So that's positive 2 times q plus 1 to the power of minus 2 minus 1, which is minus 3, right? So then we end up, if we simplify, with 2 over q plus 1 to the power 3. And then I normally leave the answer in the form that the question came in, but we started with a natural log, but this is just like a simplified version. This is the same as positive 2 q plus 1 to the power of minus 3. Okay, excellent. That's the third derivative. Then if we go and calculate the second derivative, in this case, we just have an exponential function, and we need to differentiate this twice. So the first derivative would be, so notice that there's a chain rule. So your first derivative would be, if it differentiates an exponential function, you get the exponential function back, first of all, e to the ax squared, times, you do the differentiation of the inside function. So that would be 2ax, so 2ax. And then that's the first derivative. Okay, I'm not even going to bother simplifying, or I can, and then only deal with, yeah, maybe let me simplify. So that'd be 2a, that's a constant, and then I will have x times e to the ax squared. And then I can do the second derivative. I took the 2a out so that when we do because we have a product rule here for the second derivative, when we do that, we don't have to keep carrying the 2a in the calculation. Okay, you will get to the same answer, but then the other one just takes you longer, is not as neat, and then you still, if you want to simplify, you have to factor out the 2a. So I already do it there. So y double prime would then be uh, this. Okay, so here I didn't factor out the 2a, so it's fine. So let me actually do y double prime here separately with the question in this format. So that would be 2a is a constant times the product rule says I keep one constant and I differentiate the other one, and I already know what answer I get if I differentiate e to the ax squared. Remember, we've done that. So that would be e to the ax squared times 2ax. Right, so I've done u times v prime, and I'm going to do plus. Now I'm going to keep this one constant, so that's e to the ax squared times, then I differentiate that, which is just 1, and then there's my final answer. And I can simplify this and see if we get to the same result. Okay, here we have a 2a, so there's a 2a. There's another thing that is common here and there, so I can factor it out, e to the ax squared, and then here we'll be left with 2ax times x, so that would be 2ax squared plus, here we'll be left with the 1, and then you will see if you compare this answer to that answer, it's the same solution that we arrived at in there. All right, cool. So let us now go to what would be our last problem for this evening. It's problem number 20, and it's asking us to find the second derivative for this. Okay, so this is just a quotient. We have our u and our v, so y prime firstly would be vu prime minus uv prime over v squared. And then the answer that we get, we're going to get y double prime. So let's do y prime first. Okay, so v is e to the x, so e to the x times differentiation of x, which is 1, minus x times differentiation of e to the x, which is just e to the x. And then we divide by e to the x all squared. And then now that is our first derivative. To get the second derivative, we need to differentiate this. And here we just simplified so that doing our second derivative is easier, right? So that's one of the key reasons why simplifying will matter for higher order derivatives, is because to do your second derivative, it would be easier to do. So here, if you take out a common factor, you'll see it to be e to the x, 1 times 1 minus x over e to the x squared, and then it simplifies to 1 minus x over e to the x. And then now you have a simple quotient, and then you do the derivative again. That's your new numerator, your new denominator, and then you know u prime is minus 1, and v prime is e to the x, and then you just substitute in y double prime. In this case would be v u prime minus u v prime all over v squared. If you substitute everything in there, this is the answer that you will get. Okay, right. And that brings us to the end of the session. Does anyone have a question? All right. Looks like there might not be any questions. I think I'm going to stop the recording.